All right, so let's just recap this quite dense previous set of videos. I'm aware of it. So what is that we have done? So imagine we have this gas of non-interacting particles, and we decide to describe the whole dynamics as a set of individual independent particles doing their thing, okay, in their own single particle phase space. We discretize that space to be able to count and differentiate microstates from one another. And what we decide to do in order to lose some information and make a macrostate is to merge all the single particle phase spaces into only one. And we forget about which particle is in which specific microstate. We just count how many particles in total out of the large number of particles n are sitting in each of the phase space cells. So what we have in the end is a partial description of our system, which is just a collection of integers. So tell me how many of these particles are in phase space cell 1, 2, 3, up to m. And for this thing, we calculated using combinatorics what is the associated statistical weight. Okay, so this is that thing. And there was one important assumption that we did implicitly here, which I haven't said, and you have it in the lecture notes, which is we have assumed that every microstate is equally likely. Okay, so when we calculate the statistical weight of a macrostate, we count every single microstate compatible with it equally. So we don't say that some microstates are somehow more likely than others. So we have this assumption of we just count all possible combinations equally. That's what we did, count combinations. We didn't get to think about what the microstates individually are. So that's a very important implicit assumption. Just make it clear here. It's just important to mention it, but you know it has no further consequences other than being aware of it. So we calculated the statistical weight, and then we calculated the Boltzmann entropy of this specific macrostate. Particularly, this macrostate needs not be a macrostate of equilibrium. Okay, so how do you even define a macrostate of equilibrium in this setting? Well, if this is going to behave like a proper entropy, it should be the case that if you have your system isolated, so there's no energy changes, then this entropy in equilibrium should be what comes out of maximizing the statistical weight. Okay, so you can then ask yourself, what arrangement of occupations can I do so that the total number of particles is of course what it has to be, and the internal energy remains constant because you know I'm isolated. So what is, given these two constraints, what is the arrangement of particles in cells that maximizes this thing so that this thing is maximal? Okay, and we found that the optimal occupations are like this: e to the minus alpha, where alpha is some multiplier, some Lagrange multiplier that we haven't interpreted yet, and there is another multiplier that goes with the energy of each cell. Okay, and in this case, if you just take the formula that we calculated here and replace these particular occupations, what we have is this formula that we saw before, that we now have to interpret a little bit better. So n log n plus alpha n plus beta u. Okay, so let's interpret it then. Okay, so one thing that is convenient for us to do first is to just write, to just realize or remember that the total number of particles is equal to the sum of the ni's, and in this equilibrium configuration this is going to be e to the minus alpha, e to the minus beta, epsilon I. Okay, and what I'm going to do then now is to take the logarithm of this log n. So here I have this product, so I can take this like outside of the sum if you like, and when I do the logarithm of this I get minus alpha because it's to the minus e to the minus alpha, and then the second term I have to, well, I just have to write it like that. So it's the logarithm of whatever is in there, which is the sum of exponentials. Okay, fine. So let's differentiate this thing. Okay, so if I differentiate a constant, I get a 0. Okay, now this thing, well, it's just differential of alpha. Now that thing is a logarithm, so the differential is 1 over the sum from 1 to m of this stuff. And now I differentiate the numerator, and this energies of each cell is just a constant, right? So what is changing, if anything, is this beta. So what I have is just a minus. Wait a second, is it a minus? Let me just check quickly the lecture notes. Yes, it is indeed a minus. Okay, so what I have here is the sum from 1 to m of this ei with a minus. I put it here, multiplying the overall thing, e to the minus beta ei. Okay, so now I can maybe put this on the right hand side. So the alpha is going to be minus this thing. Now I have to interpret. Well, let's just write it like that. I will just make a little bit more space and try to move the differential here. Okay, so what is it that I have here? Let me multiply and divide the numerator and denominator by e to the minus alpha. Now you will see why in a moment, or maybe you already saw it. So what I then have is here ei and e to the minus beta ei. Okay, so this thing here, right, you recognize this is e to the minus alpha, e to the minus beta ei. So what I have here is the sum of the individual cell energies times the occupation of each cell. And in the denominator, I just have the sum of the cell occupations. So what I really have is that. So what I really have is the internal energy divided by the total number of particles. So that's the internal energy per particle. That's what this differential of alpha is, okay, with a minus sign. Okay, that's the first thing to take into account. Now I have some old things here. I will just remove that. And I add another page. So remember, we want to interpret this formula, but just keeping in mind with what we just saw about differential of alpha. N logarithm of n plus alpha n plus beta u. And just so that you remember, what we just learned is that this guy is equal to that. Okay, just to use it when we need it. So let's differentiate this entropy. Okay, take the differential of the entropy again. I told you that n is by no means going to change. Okay, things that change here could be u, could be beta, could be alpha, but n is n. Okay, it's a closed system. In our case, always systems are closed. Energies might grow or go down. Maybe there is some heat coming in or out, or there's some work happening and stuff like that. But you know, the number of particles, and the systems are not losing particles or getting particles in. That would be an open system. That's not something we deal with at the moment, at least. Okay, so this differential is 0, and what we have is k times, here is differential of alpha times n, and differential of n, I said it's 0, and here we have beta differential of u plus u differential of beta. Okay, and I just calculated what this thing is. So this is k, and this is minus un times n, okay, plus beta du plus u d beta. Okay, so then just wait a second. Okay, I forgot something important, and I just go back, and I apologize for this. So remember here, okay, so when we were doing this expression, right, so we were differentiating, and here's the differential of alpha, and here I was differentiated with respect to beta, but I forgot to write the differential of beta. So this is coming here, this is coming there, and this is coming there. So, you know, that's there. Okay, so that's what I forgot to write, differential of beta. And that was my issue, because I wasn't getting quite what is written in the lecture notes. So what you have here is d beta. Okay, so this n goes with this n, and you get minus u d beta, and here you have plus u d beta. So this whole thing goes away with that thing. And what you get in the end is k times beta times differential of u. Okay, so that's what you get. So fine, this is this is kind of fundamental thermodynamic relationship in statistical mechanics with Boltzmann entropy. And from thermodynamics, just comparing when we have the true and good old entropy, what is the fundamental thermodynamic relationship in terms of the natural variables of entropy? Remember, we did this a million times, okay? So differential of U is TdS minus PdV, which means that ds is 1 over T du, okay? And then plus P over T dV. Okay, that's what you know from thermodynamics. And this is what we just got from this weird statistical thing. Okay, so how does one thing compare to the other? So when I did this differentiation here, yes, when I took differentials here, one thing that nobody probably would have thought about is that when I'm differentiating, say, this sum here, I differentiate it with respect to beta. Okay, but at no point did it occur to me to differentiate with respect to m. I just said, if I differentiate the energy of each phase space cell is going to remain constant, and of course the number of the phase space cells is going to remain constant. But this is actually not necessarily the case. Imagine that this you have a process in which your system, maybe it's a gas in the box, your system expands and the volume changes. So if the volume changes, the single particle phase space will get additional cells because the volume is changing, it's growing, let's say, or it's shrinking. Then you will lose some cells that you have. So this thing could, in principle, change, but it's not changing. So because it's not changing, in a way, you can say that this thing that you have here, okay, it's the partial derivative of the statistical Boltzmann entropy with respect to U at constant V, at constant volume, because I'm saying that the number of cells in the single particle phase space is not changing. Okay. So what is the partial derivative of the true thermodynamic entropy with respect to the internal energy at constant volume? Well, you can see it here is 1 over temperature. Okay, so then the thing is it true that K times beta is equal to the inverse temperature? That would be the case indeed if SB were to be equal to S. Okay, and this is what we have to kind of try to make sure of. Okay, so for a moment, let's just assume that indeed Vita, this Lagrange multiplier, is actually equal to the inverse temperature multiplied by 1 over K. And we're going to see that this is indeed the case when, instead of having or trying to look for the equilibrium configuration that maximizes statistical entropy for only one system, we're going to take two systems together and we're going to do a adiabatic insulation over both of the systems. We are going to find the equilibrium occupations, and we're going to see that the solution is such that the Lagrange multiplier beta of the first system has to be equal to the Lagrange multiplier of the second system. So it makes sense to think of that as the temperature, because if you take two systems together and you wait for equilibration, the temperatures have to be the same. Okay, so let's see that in the next video.